Okay, so more time on this application of what we've been doing to, here, I don't want that, okay. All right, so I've been looking at these, just the simplest way of dealing with trying to model an entity that moves around. And that's a little bit different than the kind of queuing-like systems that we've been studying. So if you recall, the the basic idea is that why is my mouse not behaving? So like you start off somewhere and you go somewhere else, and the key difference between this and some of the more traditional ways is that, namely time step, is that the time between, say, when you start and when you end, that is the time between anything that happens, is an arbitrary double value, an arbitrary amount. Whereas in a time step world, if you adhere to the methodology, then things can only happen at discrete time points. The difference between discrete time and discrete event is that with discrete events can occur at any time whatsoever. And I mean, it turns out that that's, if you've ever solved differential equations, remember those?
I try not to.
Yeah. Well, if you remember, there are some differential equations that are difficult to solve analytically, and so there are numerical methods. The first numerical method that was tried or was used is something called the Euler method, and the Euler method is basically equivalent to what a time step model does. And if you have any experience with this, you know that there are things called stiff equations in which the Euler methods fail spectacularly. And there are situations in time step models where roughly the same thing happens. And so that's why one of the solutions in differential equations is something called the Runge-Kutta method. The challenge with that is that requires you to look into the future. That is, it requires you to know for sure what your function is doing in the future. And for a simulation, that's not a legal type thing. Okay, so this is our kind of core event graph, where the idea is that we have this mover component, and at some point it hears somebody's going to schedule a move to, say, go there, and then in response it's going to schedule this start move event, which is going to update its state, and it's going to schedule the end move event based upon how long it's going to take to get there. The key to this is something called the equation of motion. So the equation of motion is an equation that describes where the particular entity is at any point in time. And so the thing that allows a discrete event approach on this is to back off from the idea that the location is a state, or that is, location is a direct state. So location cannot be a direct state in a discrete event world, because if you're moving in a continuous way, the location is continuously changing, and that's an inadmissible state. So if you have an equation of motion, however, what is it that remains constant throughout the maneuver, regardless of what the equation of motion is? What stays constant are the initial conditions. So if I have an equation of motion, I have initial conditions, whatever they may be. And so this also holds for more complicated equations of motion, which we won't get into because that would require more time than we have here. But the same principle applies. That is, the quantities which remain fixed over a certain period of time are the initial conditions of an equation of motion, whatever that equation of motion happens to be. And if that's the case, then not only can you have a more, at least in principle, a more efficient way of representing this. And that is, instead of saying, okay, do you see me now, do you see me now, do you see me now, the way the time step does, you just immediately advance time to the next interesting event, skipping over the parts where everything stays constant. But furthermore, what it also allows you to do is actually represent in a more detailed way the continuous motion. That is, continuous motion is more accurately depicted in a discrete event model given an equation of motion than it is in a time step model. Because in a time step model, I can only tell where the thing is at these specific points in time, and I can't tell you where it is in between because those times in between don't exist in a time step world. Okay, so this was our mover, and then the idea here is that given a component with an equation of motion, how does the thing move? So what this does is this models sort of a basic maneuver, that is getting from one point to the other in the correct state and maintaining the correct state in between. So the first example of something which can direct this is something we called a path. I called a path mover. You can say, what do you mean we? Me. Path mover manager, meaning that we specify a path, and that's one of the parameters, and the state is kind of where it's going to go next. And the rule is you go from one waypoint to the next. So the idea is that, so like may start here, and I say go here, and then go here, and then go here, and then stop. So it's supposed to go here, here, and then stop. So these waypoints are what the parameter is, and as I mentioned last week, if you look at this sort of as a programmer, if you have sort of a fixed set of things that you're going to do, the natural thing to think of is a for loop. But the reason that doesn't apply, that won't work here, is because in this discrete event world, everything happens at events, and events occur in 0 time. So if we try to put a for loop in, then all of that will happen in 0 time. And what we want is we want to say, okay, I'm going to start move here. Sometime later, I'm going to show up here. And then at that point, I'm going to go to the next destination. And
In the for you can put like a delay function, right?
the,
In the for you can put a delay function, there are function built-in function in the for windows, right?
well,
Like a thread, like a read.
you can try to do that, and you're welcome to try.
We can try.
And the thing is that in the discrete event world, everything happens at events. And so within an event, there's the way that you proceed from one event to the next is through the event list. So the only way to move time is for the event to be finished and the event list to process the next event. That's the only way that time advances.
Okay.
So yeah, so this is not threading. Threading is a different thing.
Oh yeah, no, I mean,
Yeah, but but it's important to understand this, so that these events make a state transition and then schedule whatever events, but then time is going to stay fixed at that event until the event list gets its turn.
okay,
So so that again, it's a it's a particularly for things like this, it's a different kind of mechanism. one of the, well, the anyway, yeah, so the idea here is that in this simplest path mover manager, the key thing here is, and this isn't the, this is a way to do it. It's not the only way. So the idea here is that this has an event called next waypoint, and what that does is that says, okay, let's advance our index to the next item of the path. Let's get the next waypoint from that path, and then pass it as by scheduling the event move to. And then, as you notice, that then it doesn't schedule anything. So the idea, this is designed with the idea that some other component is going to hear that move to, and then eventually come back with an end move event. And so here are the two components. They're listening to each other. So, and the other thing to remember is that in this methodology, the run event is where everything gets kicked off. That is the only special thing about an event. The only special event is the run event, because that's what gets put on the event list at the very beginning by the, and why why the main method? Why? Because back at Bell Labs, the guys who wrote C said we're going to call it main. There's no other. I mean, it's a completely arbitrary name. Likewise, run is a completely arbitrary name. Why? Because Shrubin, the guy who invented these, said, I want it to be run. So, that's the, but every, other than that, it's in the implementation, there's a separation between the reset and the run method. But other than that, it's treated exactly the same as any other event. And that goes back to the idea that the event list will keep processing events as long as it has events to process. So the other consequence of that is that you can look at an event graph and decide whether or not anything beyond run is going to happen. And the way to tell, like if all I had was this event, this component, then the run event is going to happen and nothing else, because it doesn't schedule anything. So what the event list will do, if this is all if this is all I have, the run event will be put on the event list. It'll perform these state transitions, but because it doesn't schedule anything else, the event list will be empty after that, and so nothing else will happen. However, if we look over here, in this particular case, as long as the start on run is true, then this run event will schedule the next waypoint event, which in turn will schedule the move to event with an argument of the next waypoint. Then, because this component is listening, it will hear the move to. It'll say, okay, now this is my destination. I will schedule a start move event. The start move event sets the initial conditions for the equation of motion, also figures out how long it's going to take, schedules that end move event, and then at some point, the end move event will occur here. It basically sets, now it says, now I'm at my destination, and then my velocity is now 0. But now, because this is listening to the mover, it will hear the end move event, and then as long as there's another item in the path, it will schedule the next waypoint, and that cycle will keep going until what? Until I run out of waypoints, and then this will not get scheduled, in which case if this is all there is on the event list, then it will empty out, and that's all that there is. So again, once the event list is empty, so the way to an implementation of that is, just very straightforward. We have our path, which is a parameter, because that's going to stay fixed in this, for this particular one. The other parameter is this Boolean that says start on run. And then our states are the next index and the next waypoint. And they're a little bit redundant. Actually, all I need is the next index, but what's useful to have this as a state is just to, when debugging something like this, because it's going to fire a property change, I can listen for that and make sure and see what waypoint this is sending it to, so that it can actually get to the next one. So here's the next waypoint event. Again, increment the index, get the next waypoint, schedule the move to event with the next waypoint as its argument. And then the end move simply says, okay, if we have another item in the path, and as with all modern languages, you have to be careful of the off by one business. So that's why you see what would happen if I didn't put the -1? I get an array, at some point I'd get an array index out of bounds exception, because I would increment it to the length of the path, and that's not a valid index. So that's the infamous off by one. Why do we have the off by one? Because again, these geniuses at Bell Labs decided they would have zero-based indexing. They had a really good reason for it, but because they were working on these really tiny little computers, and they had to save every command that they possibly could. And this saved some commands at the assembly level. So, and thereby sort of introducing generations of off by one errors for the foreseeable future. Because no matter what you do, you're going to get an off by one error at some point, guaranteed. And if you haven't, it just means you haven't been programming enough. Okay, so here's an example of this. We'll create a path here. So my first waypoint is the origin, and I'm just sort of cloning my 0 point, and I'm going to these different places, and then I think the question came up: does this go back to the original location? And the answer is no, because the Path Mover Manager, the idea is that they don't have any. How should I say? They're only sort of vaguely aware of something else. That the only thing they're aware of in the other component is that they have a move to event, and that they have an end move event that they're going to hear. That's the only thing that they know or care about. So if there were another component other than the one that we've written here that produces those events and responds to them like that, then this same Path Mover Manager could interact with that. So if you want it to go back to the original location, we can simply send it back to its original location. That's how you would do that. So this will go to these different places and then stop. So here's where we have each of them listening to each other, and we're just going to have we're going to listen to both of them with a simple property dumper as the true argument. The constructor for simple property dumper is overloaded, so if it's just empty, it'll just print the properties. When you're listening to more than one component, it's usually helpful to put the true in, and what that does is that also lists the component that's firing the property change for you, so you know which one it is. All of this is just to kind of test this thing. Notice that we don't have to stop it, because the way this is going to behave, supposed to behave, is that it's going to go, and eventually it's going to reach the end of the waypoints, and then it's going to stop. So will it do that? Well, at least it's stopped. So we can, again, we always like to print out the components just to make sure that they have the parameters that I wanted. Okay, so in this case, the parameters are the path, and it put the right things in, start a run was true, and that's usually just for testing. Typically, and again, these particular components are just, they're the simplest ones. They're a little bit, they're really just to kind of illustrate this. But then, okay, so we see here's, so here, this is what the true. So our mover is initializing its state. That's okay. Our simple path mover manager, it's initializing its state, so it doesn't have a waypoint, and the next index is -1, just because when you click it up, it's going to be 0. And so now, and it's scheduled next waypoint. So next waypoint says, okay, notice the difference in capitalization. Next waypoint with a capital N is the event. Next waypoint with a lower case is the state. So it goes from not something to 0, the origin, that's where we told it to, and the next index is 0. And now, okay, so the move to event was scheduled as the path mover manager, but now we see that the simplest mover now has its current destination, what I told it. So that, that shows that at least the listener part is working. And that's important because it's just too easy to be listening for the, like, for example, if the arguments don't match, then, and you think it's supposed to be listening, then it won't hear it. Or, I mean, it'll hear it, but it won't respond to it. Or if you accidentally fat finger the name of the thing, it'll, that's unfortunately one of the common things. So that's why it's useful to be debugging it like this. So start move, the velocity and the start move time. And then we get an end move, okay? And then notice that the end move event, see look here, so there's just the end move event is here, the end move event occurs, and then now there's the next waypoint in the simplest path mover manager. Why? Because when the end move event occurred over here, it got heard over here. The path lane, there was another path, so it scheduled the next waypoint. So it goes, so basically kind of goes, and then finally, at the end, it winds up as where we started. Okay, so the idea now is that, well, what if we wanted to do something else as a rule? Well, let's see. What if instead of just stopping at the end, we wanted to keep going? In other words, we wanted to, I call this a patrol. So what if we wanted to patrol by moving from each of these waypoints to the next? So what's useful here is that, so we have our path mover manager, and it has almost everything that we want, except we want a slightly different rule. And so instead of, and the key thing here is the next waypoint. So the next, from the end move to the next waypoint, we say we're going to schedule the next waypoint only if there is a next waypoint. And if there isn't, we're going to stop. So what if we wanted to go back to the beginning and do it all over again? Well, okay, now remember that so here, notice the connector here. This isn't a listener, this is a subclass, and it just, because of the size of these things, had to do it sideways. So the patrol mover manager is we're going to do it as a subcomponent of the path mover manager. And so what we're going to do is completely override the end move event by scheduling the next waypoint event unconditionally. And only now the main difference is the state transition for the next index is not just to click it up, but to click it up modulo the length of the path. This is actually one of the cases where the zero-based indexing is actually convenient, as it turns out, because a modulo arithmetic goes from 0 to 1 minus that. And maybe that's why, why they do that. So think modulo arithmetic. And so this will just keep going and going until we're done. And again, the idea here is that we just have to override these two methods, these two events, and then same thing with the listening. So there is an implementation of it here somewhere, I think. Come on. Okay, so we're going to extend simple path mover manager. And again, we have our our master constructor, our zero argument constructor. We just call the super on that. And so the difference is now our nmove event, which I should have an override on, says we simply unconditionally schedule the next waypoint. And then we should have an override on this as well. And now we click up the next index, but then we modulo the length of the path. Now here's the thing. As a subclass, this does not have direct access to the path variable because that is declared to be private in the superclass. Right, then that's by design. But it has a getter, so we can use the getter to get the next waypoint. And this is all that we need for that. And so now we have to be careful because now we need to stop the thing because if we don't stop it, it's just going to go forever. So I'm going to tell it to stop after 10 nmove events. Okay, so again, we have it gave the parameters, again, run, and the idea here is that when we go back to our original location, the minus 4030, what we're looking for, so everything up to here is going to be identical to the previous one, but now we're going to move to the original location, the minus 4030, and when we get there, okay, so there, the next way. Yeah, so now when we get there, the nmove event has put us at our original location, but now instead of stopping, we have our next waypoint. And then now we go back to the first item on the path, which is the origin, and then we just keep doing it and doing it and doing it until finally, here's our 10th nmove event, and then that's when we stop. Okay, so now those are two kind of the simpler rules. Now, here's another one. The rule here is that pick a random location and go there. God bless you. Pick a random location and go there. When you get there, pick another random location and go there. And when, just kind of keep wandering around these random locations. This This is something that's, sometimes people kind of use this as a way of testing some kind of search thingamabobs. It can be useful. So instead of kind of going, basically it's sort of randomizing. So the idea is now we have our parameters are going to be a coordinate generator, a coordinate generator, which is going to be just an array of random variates. We're going to have one random variate for the x location, one random variate for the y, and those are going to generate random x, y coordinates. Again, we have sort of the start and run thing to say whether we should do this right away. And now our only state is going to be where we go next, because there's, unlike the patrol and the path, which had a fixed set, here there's no fixed set. So the idea is that now at each end move event, we simply generate the next waypoint from our array. So here again, our state is our next destination, and so we will schedule our next waypoint, and our next waypoint is simply going to be randomly generated. We pass that destination to the move to as we did before. We listen for the end move event and schedule the next waypoint, and we just kind of do. And so we're going to keep doing this, and then somebody else is going to have to make us stop. And again, we're going to listen to each other. And what does that look like in terms of, let's see, yeah, there it is. Okay, so the simplest random mover manager, we have our parameter is an array of random variates, and the start on run, and then our state is our next waypoint. Again, just sort of a master constructor and a zero argument constructor. And so here what we're, just to kind of be green and recycle things, we're going to basically make sure we instantiate our next waypoint and then simply change its state by doing set location instead of instantiating a new one. So next waypoint simply says, okay, so again, we're going to do the previous waypoint, and we're now going to set our location to be the generate method from the 0th index, and the generate method for the y to be from the one with index 1. And then we're going to schedule the move to, passing that point. And remember that because these point 2Ds are objects, we want the getters and the setters, if we have them, to be copies. And so there are a couple ways to do that. The most straightforward is to clone it. If we clone it, we have to cast it. And so it's important to where is it here? Oops, this should be a get. See, we want to preserve encapsulation, so we're actually passing a copy of our destination. So how do we kind of test this? Well, we start with an array of random variates. So I'll start with a uniform minus 50 to 50, and then a normal with a mean of 0 and a standard deviation of 30, just to kind of make it spread out a bit. Now I think, what I wanted to show, so remember that starter, usually we have kind of a false start on run. And so if we don't do anything else, then it's just going to kind of sit there. So a way to do that is to have another class that's going to do that. So here I created an inner class, call it mover starter, and it has a single, oops, it has just a start that says we're going to start at this time. And so its run event is going to schedule the next waypoint at the start time. And yeah, so this should be private. Okay, so what that's going to do is, so I'm going to instantiate that. I'm going to say I'm going to start moving at time 2.5. And and now my random mover manager is going to listen to that, and because it was false, nothing is going to happen until time 2.5. So that's what I'm looking for. And then again, I'm going to stop after 10 end move events. So let's see what that does. We at least stopped, so that was, at least we stopped. So let's see what's going on here. Let's find it. Okay, so now we have our simplest mover, we have our simplest mover manager, and our mover starter. So, and the order of these should not matter, because the run events should be independent, and if they maintain encapsulation, they should not be affecting any other components. So after we spin with the run events, again, now notice, okay, so here, finally, with the mover starter scheduled, when its run happened, it scheduled next waypoint at time 2.5. Now the event list now moves to time 2.5. It's scheduled, the next waypoint event occurs, and then that in turn triggers the move to event for our simplest random mover manager. And now, if you notice, these coordinates are these ridiculous numbers. We could maybe override the point2D's two-string method just kind of prints the whole shebang. We could maybe subclass that, override those to have shorter things, but again, this is just for testing purposes. We see that we are being sent to both positive and negative coordinates at various random, they look sort of random. How random are they? Well, actually, once we kind of finish this, we're going to kind of peel back the hood a bit on what's happening with these random guys. So again, at the 10th end move event, we finally wind up at this location. So the idea here is that we don't have to modify our mover in order to have, at least we've seen 3 different behaviors, if you will. Behavior is kind of a fancy, wouldn't necessarily call these behaviors, but they're rules. They're rules for how to move. And the point is that using this event listening now allows us to have different rules without having to modify our mover guy. Now, if we had a different mover that maybe had a different equation of motion but simply responded to the same events, then we wouldn't have to modify our managers. So that's that I think is a useful component-like thing. In other words, if you want to upgrade your graphics card, for example, you shouldn't have to replace the whole computer. Okay, so before we leave, I do want to, the question is, if you notice that one of the things that we did was we were computing the velocities. We were noticing when different events were occurring, and we were implicitly assuming that those were correct. But how do we know those were right? So that's why it's important to kind of be able to do this by hand, so we can check it. We can kind of do the calculations and say this is what the velocity should be. This is when it should arrive at the destination, and this is where it should be, say, at some intermediate time. Okay, so here's the. Okay, so if we start at, say, 20 minus 30, and we'll say at time 0 it starts moving to this destination at a speed of 30, and the three questions we want to answer, which we probably will only be able to get one or two before time runs out, is, well, first, probably the most important, what is the velocity? Okay, so that's the most complicated one, right? So how? What? Yeah.
No, never mind.
Oh. Yeah, so, okay, so to do the velocity, we start by subtracting the destination from our location. So that's minus 1050, minus 20, minus 30. So minus 10 minus 20 is minus 30. 50 minus a minus 30 is plus 80. And now we need to find the distance. It's the Euclidean distance, so it's the root of the square of these, which is minus 30 squared plus 80 squared root, which is 10 root 73. Because my phone is on the fritz, I have to keep it with the rat. And now, okay, so what's the velocity? The velocity would be the vector difference divided by the norm times the speed. So in that case, it would be the minus 3080 over 10 root 73 times 30, and which turns out to be this, which is, approximately this value. So if we were to then say, all right, as long as we trust our calculations here, okay, then we can say, when we run it, is this the velocity that comes up? Because we can look at, say, well, what velocity did they come up with? Did they come up with this one? Assuming that we did this right. So again, okay, so what's the travel time? The travel time in this case would be the distance divided by the speed. And so that would be, in this case, root 73 over 3, or approximately 2.8 something. And then now we can, to say, where are we at time 2? Again, we apply the equation of motion. In this particular case, the equation of motion of a constant velocity is our starting location plus the velocity times the elapsed time. And so at time 2, we have our starting location plus our velocity times the elapsed time, which would be 2 minus 0. And then we just kind of unravel that to get approximately that. So how can we evaluate that? Well, what we can do, and what sort of the next sort of step in developing these simplest components to a more useful ones, would be to recognize that even though location it cannot be a discrete event state, we would need to add an implicit state, which would simply be returning the equation of motion based upon the state. So remember, the state consists of these three quantities, 2 of which are vectors. So it would be a total of 5 values. And knowing those 5 values, we can compute where the thing is at any given point in time. And so the importance of that is that, and one of the questions that of course come up in this as well, you seem to jump from one location to the other in a certain amount of time. What if something happens in between? And that is a very legitimate question. So and is partly answered by this last item, namely, in this particular case, if some event were to occur at time 2, and that event would need to know where this particular mover was at that intermediate time, if we had this implicit state added to our component, then we would be able to process that. In other words, if an event happens, the only thing that can occur is an event. And if an event occurs while a maneuver is in the midst of its traveling to another place, then I can know exactly where it is. And so if, for example, let's say the event might be, let's say this is like a vehicle, and the event might be it encounters an IED. Well, on its route. So it's not going to make it to its destination if the IED is successful. And so it's going to have to, basically it's going to stop where that IED was. And so what could cause that? Well, some other event. And how can we model that type of situation? Well, that is what we're going to talk about tomorrow.